Hello everybody, my name's Ken Newhouser and I've been a geologist most of my life. I've studied geology for at least 50 years and I have taught geology for 40 years, and out of those 40 years, one of the favorite things I've had about geology is going in the field. I kind of consider myself a field geologist. I know that one of the main reasons why I got into geology, because my teachers where I went to school took me on field trips. I found it to be the most exciting part of geology. And during that time when I was doing geology, I've been doing research in the field. I've been teaching field trips like this, and also just classes in different parts of the United States over these years. So I felt it really important that I get together and create a field trip that would be more virtual in case you don't have the opportunity to go into the field. And it's my goal to instill in you the desire to go out in the field like I did and really get to enjoy the geology. And so we're down here south of Hays, Kansas right now, near the Smoky Hill River, little town of Shenshin if you want to look it up. And I'm at what's called a typical rock outcrop. If you look at the rock layers here to your left, you'll notice you see different kind of bands or layers of different colored rocks. Well, we call these outcrops. And in this virtual field trip, I'm going to take you to a number of geologic stops, as we call it, different types of outcrops. Now, some of these outcrops, as I refer to them, they're going to be buildings maybe on Fort Hays State's campus. They may be outcrops just like this, or some other really strange, interesting geological features that you may not think about in western Kansas. I'm sure for you, what you want to understand about this virtual field trip is what are you going to see? What are you going to do? When I take you to these outcrops through a series of slides that you'll see in a PowerPoint, there's going to be pictures of rocks like this. We'll zoom in on actual minerals or fossils, and I'll be describing all the nuances about those features that you see and why they're there and how they formed, when they formed, and stuff like that. But there'll also be other imagery. There'll be geologic maps, there'll be images from Google Earth that you'll be zoomed in on the surface of the earth, and so I mix it up. And again, this particular virtual field trip, it might run anywhere from 50 minutes to 60 minutes long. And you'll be able to easily follow along with this PowerPoint that's going to be put into a YouTube presentation. And so, again, I hope that you enjoy this trip. And it's certainly like any other kind of online class, you're going to want to have questions. Feel free to email me or even give me a phone call, and I'll do everything I can to answer the questions that you might have. So, yes, this is a nice virtual field trip, but remember, I'm a field geologist, and if you get the chance, go out in the field and enjoy it and have a good time. Thank you very much. I hope you enjoy the class. All right, welcome class to a second series of a totally virtual geology field trip. This particular one's going to focus on Ellis County and more so in the northern part of the county. I'll say more about that in a bit. But first, in this opening slide, there's some bullets here of information you'll need to know. Again, my name is Ken Newhouser, and I will be presenting this kind of virtual presentation today, a series of slides in a PowerPoint. And your job is to watch, listen, of course, take notes as you move along through this YouTube presentation, and hopefully enjoy all our geological stops. Now again, when you're done, be sure that you review and study your notes. Look over the pre-exam study sheet that I'll have posted out in Blackboard. And when you're ready, of course, go online to Blackboard and take the exam. And notice you'll need to finish this exam within 14 days after you take this trip. Password, of course, is listed here for this particular Ellis County trip. It's Katobi, all lowercase. And you need to receive at least a 60% or higher to pass the course. And you can read the rest of the bullets here as we move on in. So, slide number 1 is a Google Earth image, kind of centralized over the United States. And of course, you can see Kansas there that's highlighted. We're going to focus in that area on this particular field trip. Now, I'm going to start out on this trip near Hays and within Hays, Kansas. And as we progress, I'm going to go to all the places kind of highlighted with red stars and you'll see the inset green color change as we move through these. So we'll go into Hays, Kansas first for a variety of different stops, and then we'll head on towards eastern and north part of Ellis County and loop our way around kind of counterclockwise north of Ellis and end our field trip. All right, so slide 2, again, as you look at it, is a kind of a Google Earth outline of Ellis County, and I've shaded in the area that's the focus of this particular trip. Now slide 3 is a close-up, again in Google Earth, focusing on Hays, and you're looking northward. The main highway that runs through Hays is Highway 183, and our first stop's going to be down around Fort Hays State Campus. All right, now slide 4, again, is a Google Earth shot that kind of, on the left-hand side, focuses on 3 different buildings on the Fort Hays State Campus that we're going to look at. Tamatic Hall, Forsyth Library, and Albertson Hall. And then lastly, we'll leave the campus and head down along one of the other roads in town here, the Schmidt Rocks Work, and take a look at some of the interesting geological features at that site. All right, slide 5 I utilized to kind of go over some new ideas that you may not be familiar with in geology. On the left-hand side of your diagram, you'll see what we call a geologic timescale. Now, today is Tuesday, the day I am taping this session, and of course we've known these days of the week, Sunday through Monday, since we were children. We know the days of the week, we know the months of the year, and we are able to communicate time by doing that. Well, geologists use their geologic timescale to do the same thing. Now, on the very bottom of the diagram, we'll look at some names that you may not be familiar with, but we always put the oldest time periods on the bottom of our diagram, and as we work towards the top, they get progressively younger. Now, I've starred 4 different spots of 4 different geologic time periods here with arrows pointing to them, starting with the oldest at the Permian, working our way up through the Cretaceous, then eventually the Miocene, and lastly the Pleistocene. And those represent rock periods where rocks were quarried out, or we're going to see in terms of those time periods on different stops during this trip. So occasionally you'll see this geologic timescale in different parts of this presentation. On the right-hand side, I have 2 examples of what are called graphic stratigraphic columns. Again, we put rock layers on the bottom of these diagrams, and as we work towards the top, they become progressively younger. Now, there are some names in here that you'll have to get to know their ages, which particular time period they belong to, and a number of other features about these rocks that I expect you to know for the exam. As we look at the outcrops today, some of the ones I'll focus on this trip are more in the middle of the diagram, particularly the stratigraphic column in the middle. It's in white. We'll be looking at an outcrop at one of the stops that's involved in the middle, where you can just barely see Blue Hill, Shale, Codell, and Fort Hays. Those are more in the upper part of the diagram on the right-hand side of slide 5. All right, a second thing on slide 6 that I'd like you to get to know about is what's called a paleogeographic map. Now, the prefix paleo means ancient. So let's say today you went and you got a big atlas of the world out, and you could find North America, and you could see where the coastlines are and where the lakes are and where the oceans are and stuff like that that surround North America. What if we could go back in time, millions of years ago, to a particular time period and look at an ancient geographic map? Well, that's referred to as a paleogeographic map. The one I have shown here on the left goes back to the Cretaceous period, around 65 to 70 some million years ago, and what it might have looked like at that time period. Now, we create these kind of maps by looking at the sedimentary rocks that we see in road cuts and outcrops across the countryside. And we can figure out where the ancient shoreline was, which way the rivers flowed, which way the wind might have blown, by the distribution of these rock types as we study modern outcrops today. So remember that a paleogeographic map is an ancient type of, of map like you'd see in an atlas. Okay, slide 7 is our first official stop on the Fort Hays State campus. This is the building known as Forsyth Library, and you can see these light-colored rocks that make up the walls and some of the ledging around the building. This is rock that is of the Permian age, and the formal rock unit most often used here is the Cottonwood limestone. So those are two things you need to remember, the Permian age and the Cottonwood limestone for Forsyth Library as part of this stop. Now we'll get kind of closer to the building. You can see that surrounding parts of the walls are these ledges, and I usually take the students to these ledges and point out some very interesting fossils that are located in these rocks. Again, this is still Permian aged Cottonwood limestone, and if you look closely at the Cottonwood in slide 9, you'll see these little white kind of almost rice-like shaped features. These are actually skeletons of a critter called fusulinids. These are a type of zooplankton or animals that were floating in the upper part of the Permian seaways during the Permian age. And when those organisms died, their skeletons kind of rained down and dropped to the bottom of the seaway, and they were buried in these limey muds, and when that happened, eventually it was turned into a limestone rock, which we of course call the Cottonwood limestone. So let's kind of take a little step back to, again, one of those features I talked about, a paleogeographic map. This is a paleogeographic map on the left-hand side of slide 10. If you look in sort of the middle part of the map, you can see a small green finger-like extension that comes up into roughly where Kansas is. Well, in eastern Kansas, we had this warm, shallow seaway that was just teeming with these fusulinids. And of course, when they died, they dropped to the bottom of this seaway. And once buried, they were hardened into a sedimentary limestone. On the right-hand side of the screen, I have a number of images from some of the quarries in eastern Kansas. I think these are near Paxico. This is the Cottonwood limestone quarry, and you can see various stages of the operations of removing this material that's used in a variety of things, in building stones, of course, like on Fort Hays State's campus. Slide 11, again, shows us our geologic timescale on the left, and an inset map of another quarry for the Cottonwood limestone in Chase County. The inset map in the top right in red is where Chase County is located. Below that is a picture of a quarry, and at the very bottom right-hand side of the screen is an actual outcrop of the Cottonwood limestone. And the arrow is pointing to the Permian time period. So kind of in kind of review again, the rocks in Forsyth Library of Permian age, Cottonwood limestone, and they're made up of lots of little fusulinid skeletons, fossil skeletons. Now here's what they look like up close in a hand specimen. Slide 12 shows you in the upper left-hand corner these small little white oval type fossils. They're not rice. Remember that they are not fossil rice. And over on the right-hand side, we see where some of them actually have weathered out of rocks, and they're sprinkled across the surface there. And there's a penny in both these images for scales. If you look very closely with a hand lens or under a microscope, you can really see the detail of the skeletal structure of the fusulinids. So along the bottom of this slide are a schematic, some drawings of some of the different types of chambers and terms used to describing these single-celled plankton-type organisms. On the right, more of a cross-section images, and in each different fusulinid, there's different species, have different kind of characteristics to those skeletal structures, and that's how we can use them in terms of age dating things. Now slide 13, it's a busy slide. I'm going to spend a little more time on this slide. It's kind of our second stop while we're on the campus of Fort Hays State. Stop 2, and this is a picture of Albertson Hall, and you can see where the word or the lettering stop 2 is. This is the newer part of Albertson Hall. built in the 1950s. And then behind that, the taller portion is the older part of Albertson Hall. But nevertheless, when you look at the building, like all the others on campus, they have a lot of these limestones again, just like Forsyth Library. Well, there's actually 4 different types of limestones that make up Albertson Hall. Now, before I go into the names of each of these and some information about them, I want to bring your attention to the top left-hand part of the slide. This is another paleogeographic map, except this is during the Cretaceous period. And during the Cretaceous, there was a warm, shallow seaway that ran from roughly the Gulf of Mexico all the way up to the Arctic Ocean. And so sea level would rise and drop and rise and drop. And we get these, what we call transgressions. That's when sea level would rise, and a regression is when sea level would drop. And this was partially due to a number of other activities, some of which were related to tectonics and the buckling of the crust. But in this warm, shallow seaway, we had another different types of microfossils that made up the plankton portion, and they had calcite crystals, and I'll say more about what those are in just a bit. So as sea level went up, sea level went down, the shoreline position would shift laterally, side to side. And so what that does, it creates a vertical change in rock types from shale, limestone, and would repeat itself throughout there. So the bottom left-hand part of the thing is that graphic, stratigraphic column again. And so where you should bring your attention to is the upper part of the unit there called the Pfeiffer Shale. The uppermost Pfeiffer, you can see a little brick-like pattern. Those are the bricks, or the limestones known as the fence post limestone. And so we use different symbols in these columns again. Bricks for limestones, dots for sandstone like we'd see in the Codell sandstone, and of course little horizontal lines for shales. So one of the rocks that makes up, is predominantly in the younger, newer part of Albertson Hall, is the fence post limestone. And we'll get to an actual close-up of that in just a bit. The older part of Albertson Hall consists of 3 different types of limestones. One of these is the Fort Hays limestone, which was quarried out, as is the fence post out here in western Kansas. But also on the very right-hand side, the stairwell portion is made up of the Cottonwood limestone, which, as you recall from stop 1, is Permian in age. So we've got some, different aged rocks in this. Let's kind of review some of them. The fence post and the Fort Hays limestone are Cretaceous in age. The Cottonwood is Permian in age, but there's one that's kind of difficult to see in the slide. It's called the Salem limestone. And the Salem limestone is a bit gray or lighter gray type of limestone. It's Mississippian in age, and it's the same rock that makes up pretty much all of Tamanic Hall. Now, I've inset a picture in the bottom right of Tamanic Hall. That's why I mentioned it was, Tamanic was one of the kind of visits, so to speak, on this field trip. And if you look at that inset, you can see that lighter colored gray. Well, just there in the very middle, back up in Albertson Hall, you can see a small lower part of the building. It is much more weathered through the ages. It's, it was, that part of the building was put up there in the 1920s, and so it's been gone through a lot of changes in time. So, little review of the final thing. 4 different types of limestone make up Albertson Hall. The oldest is the Salem limestone, which is Mississippian. Next in age is the Cottonwood limestone, which is Permian. And the last 2 are Cretaceous age, fence post limestone and Fort Hays limestone. All right, slide 14, kind of a geologic timescale again that I mentioned earlier. Albertson Hall, as a repeat again of different ages of limestones. The Mississippian's the oldest, Permian is the next youngest, and then lastly 2 different types of Cretaceous age rocks. Where they come from, the oldest Mississippian Salem limestone is from Indiana. The Cottonwood limestone, which is Permian, is eastern Kansas. And out here just west of Hays, Kansas, up on the hills to the west of us a little bit, are quarries where we quarried out fence post limestone and, of course, Fort Hays limestone. So 3 different geologic time periods and various numbers of quarries that we see here in slides 14 and 15. All right, slide 16 is a close-up of the south side of Albertson Hall. It's the fence post limestone, and then you got 2 components. You've got the larger looking fossils that you can see with the naked eye. In the middle, there's kind of a coiled feature there, set up a coiled cephalopod called an ammonite. And in another spot in the top left-hand corner, you can see kind of a bivalve, kind of clam-like feature. Some of these bivalves are clam-like pelecypods, or they're oysters that make up most of the megafossils that we see in the fence post limestone. What you can't see with the naked eye is what makes up the matrix. Now, the matrix are really tiny, tiny crystals. You will need to see what they look like under a microscope, and I'll have another slide coming up that deals with that. And I might bring your attention right just to the left of that coiled ammonite, kind of a little bit more browner feature. I want to come back to that in a little while, but another interesting larger fossil that makes up the rock. Now here's a slide in slide 17. That's one of the components that make up the matrix. These are very enlarged, what we call microfossils. These are foraminifera. We kind of shorten that to foram sometimes. It makes it easier to remember, I guess. But a foram essentially means a hole. So if you look close at some of the surface texture, you can see it's just pitted with lots of these little forams or holes that make up this type of fossil. The skeletons here are made of the mineral calcite. This zooplankton precipitates these minerals out of seawater, makes up the skeleton. When these things die, they rain down to the bottom of the Cretaceous seaway. And of course, just like in the Permian with the fusilids, when they get buried and hardened, they're turned into a limestone. All right, slide 18 is a second type of skeleton that we find in the fence post. This is a thing we call a coccolith. This bigger picture you see here with these wild kind of geometric shapes, this is a modern coccolith in the modern seaways. But in the bottom right-hand corner, you can actually see a scanning electron microscope image of the exact types of coccoliths that are found in the fence post limestone that make up the matrix in this part of Albertson Hall. Just kind of unique. I always think it's pretty cool to look at the geometry of the minerals and the shapes that make up these organisms, from an engineering standpoint in terms of strength and durability and stuff. We might get to learn a lot from nature as to what might be something unique in terms of geometry to use as a building style. All right, slide 19 is another part of the fence post limestone, and I show you this one only for one reason. It was one of the largest coiled ammonites that we can see in Albertson Hall. It has been removed, it's no longer visible, but it's kind of unique, and this is something I'll show you, kind of a modern day analogy coming up in a little while. So fence post limestone, again, Cretaceous age, part of Albertson Hall. All right, now here's another kind of fence post limestone that's exposed in Albertson Hall, and again the bivalves, I've got some arrows pointing to different types of clam-like features. But to bring your attention back to this larger brown thing in the middle, this is actually a fish scale. It's pretty unique in terms of being fossilized in these limestones from the past. They tell us a lot about what kind of things were in those Cretaceous seaways. The matrix, of course, are coccoliths and forams again. But I wonder what might have been the source of this fish scale that we see in slide 20. Well, in slide 21, maybe this is the source. There's 2 different kinds of fossil fish in this image. These are actually things you can see at Sternberg Museum in Hays, Kansas. The big one on the top is called Xiphactinus. That's also related to one of the famous fossils out there called the fish within a fish. Or it might have been from the fish on the bottom in the screen, Gillicus, which is kind of another very large Cretaceous fish at that time. Slide 22, going back to another kind of megafossil we see. Instead of a coiled type of ammonite, this is more cigar-shaped, more straight. And there's an inset there in the bottom left of a kind of an artist's rendition of the main shell, and then the fleshy head and the tentacles that were sticking out. It's usually, of course, the calcareous calcite shell that is preserved in the fossil record. So again, we have these coiled ammonites and we have these straight-shelled ammonites. And here's again that coiled ammonite close up. A modern-day living relative of these Cretaceous ammonites is the nautilus. In the top right-hand side, you see a complete nautilus, and on the top left, you see a kind of a slice where they cut through, and you can see the internal parts of that. So this is kind of the same thing that was swimming around in the Cretaceous seaway. It died, ended up in the muds in the bottom of the sea and got buried, and then preserved as a fossil. And these are just kind of cool things that you find out here in these rock units in western Kansas. Slide 24, I just had to show it again. If you look at an internal makeup of a modern nautilus, the pearlescence, the detail of the chambers and how it grew in a spiral kind of pattern. In this case, it would have been counterclockwise, given the view that you have. It's just pretty. It's very cool, you know. All right, slide 25. We're going to move away from the campus now, Fort Hays, and move into a more eastern part of the city of Hays. And this is very different. This is a unique stop I take the students to show them gravestones. That's right, gravestones. So stop 3 in slide 25 is, again, a very unique stop for our students. So we get down here in the ground, and slide 26, where I take them, is to a place called Schmidt Monument Works. And they sell gravestones of all different styles and rock types and patterns of people's choice. On the top right, you can see some pretty interesting designs to different kinds of rocks. In the bottom left, just take a look at the different places that Mr. Schmidt has actually gone out to get rock types from across the world to sell to customers. The schist from Finland in the bottom left in the sunlight just sparkles from these kind of platy green minerals in there. The one in the middle, the bluish kind of banded one, comes from Brazil. It's a type of metamorphic rock, as is the schist. Very, very expensive type of stone to bring in. The more cylindrical tan one in front is probably a sandstone, I think, is what Mr. Schmidt thought. I really couldn't work on it to bust it open to kind of double check, but it to me with a hand lens looked like a sandstone, a quartz-rich sandstone. Came from Israel. And then again from the Middle East, here we have some fossilized logs. Came all the way from Egypt, so pretty spectacular. I used a slide on the bottom part of, or the bottom right part of slide 26 to start talking about some of the specifics of the rocks that they sell. Most of the rocks that are sold are metamorphic type rocks or igneous type rocks. So I want to talk a little bit about igneous and metamorphic rocks. So go to slide 27. Slide 27 is a kind of textbook diagram that shows the crust and the mantle of the earth and where plates are colliding and hitting head on in this particular image. So there's a lot of pressure. There's a lot of intense temperatures going on that you can see in this. The deeper you get into the earth, the hotter it gets. So given certain conditions, you get to a point where some of the rock melts. It turns into a liquid, which we call magma. And being less dense than the solid rock around it, it starts rising to the surface. So if this liquid magma is very, very stiff, it doesn't rise too quickly. It doesn't rise and make it to the surface of the earth. But if it's a more runny type of magma, more liquidy, it will make it to the surface and become an extrusive type of igneous activity we know as volcanoes. And some of these volcanoes can be very violent, and some are very, very quiet. And so it's something about the way in which the magmas form, what the composition is, how thick or stiff or runny the magmas are, whether they stay inside the earth or whether they come out to the external part of the earth, determine something about crystal size that I'm going to show you in the upcoming slide here. So let's take a look at slide 28. This is a close-up of a very common igneous rock type called granite. Granite is an igneous rock, And you look, you see a dime there for scale. With your naked eye, you can see individual different minerals, different crystals. The pink ones are feldspars. The gray and kind of whitish crystals are either feldspar or quartz. And the dark ones could be different types of pyroxenes or micas that are in there. But nevertheless, you can actually see the crystals. So I want to bring in this idea of cooling rates now. As this magma is rising towards the surface, if it cools very slowly, let's say because it is rising very slowly and it stays inside the earth, stays intrusive, okay? Staying inside the earth is what we mean by intrusive. We also have another word in our vocabulary called plutonic. They're the same thing. So the deeper this magma begins to cool off, and the slower it cools, the larger the crystals that make up this particular kind of texture that we see in granites. So the larger the crystal, we say it is coarse-grained. We have a fancy name for that as being phaneritic. So cooling rates determine the crystal size. Remember that. All right, slide 29, if you move to that one, you'll see now in this one, you can still see that dime for scale. Notice how smaller the crystals are. But you can still see them with your naked eye. Now, yeah, the magma is still cooling at a slower rate, but it's a little bit faster than in that last slide. So we get kind of medium grain textures, but it's because we can still see it with the naked eye. We still call it phaneritic. It's still intrusive or plutonic, but it's moved a little bit closer to the surface of the earth. It's a little bit shallower in depth, but they still have not come out on the surface of the earth. These are still granites, and we have coarse-grained granites. We can have medium-grained granites, even finer-grained granites, but they're still phaneritic. Let's move to slide 30 now and talk about those magmas that actually make it to the surface of the earth. When magma comes out on the external part of the earth, we say it's extrusive. This is part of called volcanic activity. And so the cooling rates are going to change. You're going to create much finer grained, smaller crystals that you cannot see with the naked eye. You'll have to see this under a microscope. So two different kinds of cooling rates, different kinds of crystal sizes. The fine-grained, tiny texture for this one we call aphanitic. So granites were phaneritic. This particular type of extrusive volcanic rock is called basalt. So basalt has an aphanitic texture to it, fine-grained crystals. Now when this kind of liquidy magma oozes out at the surface, this basalt magma comes out and spreads out in a fairly thin layer of material. Take a look at that inset map on the bottom left of the Pacific Northwest. The big green area represents a huge area of Columbia River basalts. These are basalts. Now when these basalts cool down, again, two things happen. They cool rather quickly, so you get that fine-grained aphanitic texture, but they also crack vertically and create these giant columns. So we call these basalts columnar basalts. And if you look at the inset in the top right, you can see an actual outcrop along the Columbia River and those big vertical columns in there. But if you take a look at this rock right in the middle, that is sold at Schmidt's Monuments work, is a new type of gravestone. It's spectacular. You can carve it. The artisans work out different kinds of features, in this case a rose. And you can also carve initials, or you can put in a little inset and put a brass plate in there, whatever you wish to have for your gravestone. Now, but kind of unique. I think that Schmitz did a pretty creative thing about bringing different kinds of unique rocks of igneous character to haze. So slide 30 is kind of pretty unique stuff in there. All right, slide 31. Now I go to the second major type of rock we find in these gravestones. They're metamorphic. So again, I have another diagram, just like the one I used for explaining the different magmas that formed in igneous rocks. It's a pretty busy slide, but don't worry too much about all the detail in it. I use it again to talk about two different variables: pressure, which is P, and temperature, which is T. Metamorphic rocks, metamorphic means change of form. Morph is form. What's changing is the crystal character. During metamorphism, rocks are recrystallized. given different pressure and temperature conditions. You can have all pressure, which is basically where you crush it under high pressure, or all temperature, which you essentially bake it and recrystallize it, or most commonly over a broad region, different types of metamorphic rocks produced by a mixture of pressure and temperatures. Sometimes it might be a lot of high pressure, low temperature, or it might be very high temperature, low pressure. And so we get a mixture of different kinds of, characteristics of metamorphic rocks. Common names that you'll hear will be schist, like that schist from Finland, or quartzite, which is a metamorphosed sand, quartz-rich sandstone. A lot of interesting kinds of things about metamorphic rocks that I'll show you in subsequent slides. So let's go to slide 32 and take a look at a common character of metamorphic rocks. They get a very layered, banded look to them, a banded kind of texture. In this rock here, you can see alternating bands of dark minerals and light minerals. It's a very common kind of characteristic of metamorphic rocks. Like igneous rocks, they consist of a lot of crystalline minerals. They're of quartz, feldspars, and micas. They're very, very hard. When you feel them, you hit them with a hammer, they're very hard like igneous rocks. This particular one that's banded is referred to as a gneiss. Gneisses are common metamorphic rocks used in gravestones. So remember that banded nature. Remember that these metamorphic rocks form deep in the crust, 5, 6, 7, 8 miles down below the surface of the earth under those high pressures and temperatures. Slide 33 is another metamorphic rock, a little bit different in its banded nature. You can see some very elongate, lighter colored minerals, but nevertheless has kind of a layered texture to it. Again, this is still a gneiss, so there's lots of different kinds of gneiss metamorphic rocks that we'll see. Again, forming very deep inside the earth. Not deep into the mantle or the core, but deep inside the crust. All right, let's go to slide 34. I use slide 34 to kind of point out one thing, and that has to do with what's the rock that got metamorphosed? What's the original rock? We call that the parent rock. And the white rock you see in the middle, that white larger slab, is a metamorphic rock called marble. Well, if you metamorphose limestones, and right above the phrase metamorphosed limestone, you can see some actual lighter sedimentary rocks. That's the fence post limestone. So if you metamorphose something like the fence post limestone, you end up with marble. So don't forget what the parent rock is of marble. That will be certainly a question on the exam. That is limestone. Limestone is the parent rock. All right, let's move on to slide 34, which at this time is a break for you and for me. Take a break and rest your hands, and we'll have this short intermission, and we'll come back in just a bit. Okay, welcome back. I hope you had a nice break, and so it's time to move on with the second half of our totally virtual field trip for Ellis County. Let's move to slide 35, and again, this is this map I showed you early in the presentation, and notice that the arrow is pointing to another site. This will be our next stop. We're kind of moving more north of Walker, Kansas at this time, and so slide 36 is our next stop. This is an actual real outcrop now, stop 4. And this is an exposure of the Fort Hays limestone of what it looks like in the field. It is underlain by another rock unit called the Codell sandstone. And you can look at the graphic stratigraphic column on the right to try to locate roughly in the middle of that column where these two units are. Again now, I want to repeat things you need to remember. The formal name of the rock units out here, the Fort Hays and the Codell, and they are of Cretaceous in age. But I bring students to this stop not just let them see what the rock looks like in the field, but to introduce the concepts of what we call transgression and regression. Transgression refers to a rise of sea level, and regression refers to a drop of sea level. And so these two kind of processes actually cause the position of shorelines to shift laterally. So over time you can get a marine type limestone developing, or you could get a near shore beach-like sandstone being deposited in the same place. So if you get transgressions, regressions, transgressions, and regressions, you can get alternating limestones, sandstones, shales within the same zone. And that's why you see the graphic of those rock units the way you do on the right-hand side of the diagram. And let's take a closer look at this. If you got a shovel and you could dig down below the road, you'd run into an older rock unit below the Codell. It's referred to as the Blue Hill Shale. Again, it's Cretaceous in age, and as you move upward in this column, you run into Codell sandstone. Well, what kind of depositional environment did the Blue Hill Shale form in? What formed offshore, out in the deeper waters, where there was a lot of mud and clay? And of course, these things, when got buried and hardened into a rock, became a shale. So what happens between the time period with the Blue Hill Shale until you go upward into Codell? I try to get my students to imagine being underwater in the ocean, watching the clay particles come in, and you're sitting around in all the muds that become the Blue Hill Shale, and all of a sudden, sea level starts to drop. And next thing you know, you're actually sitting near the shoreline in a beach. Well, what kind of sediments are coming around you now? What's kind of coming in from the land and moving along? Well, it's going to be sand, coarser sands, because you're near a beach. So as the sea level dropped, or regression, as you move from the Blue Hill up to the Codell, you see that reflected in a type of sediments and thus the rock type. So don't forget, as you go then from the Blue Hill Shale upward into the Codell, this is evidence of a regressive facies or regression, a drop in the sea level. Now the green line, there's kind of a boundary between the Codell and then the Fort Hays limestone that's above it. What happened next? Well, you're still sitting in the same spot. All right, you're still surrounded by the beach sands. All of a sudden, sea level starts to rise. Well, you're back underwater again. So now all these skeletons of things like the coccoliths and the forams I told you about before come raining down around you, and maybe some fish swim by and some other types of things. You'll see the ammonites and the cephalopods and the clams around you. Well, if you're actually seeing then in this rise of sea level this transgressive facies. So now these calcite-rich muds are deposited, and that hardens into the Fort Hays limestone. So every time you're driving around the countryside and you see these alternating changes from shale to sandstone to limestone and back and forth, you are actually seeing evidence that we use that represents transgressions and regressions of sea level. All right, let's move to slide 37. This is back to our map. We're going to move a little bit further up the road. In fact, if you go back to slide 36 and look straight north there on the highway, about 2 miles north, we come to what we see here in slide 37. And that's kind of our position arrow there with a green spot. All right, let's move to slide 38. This is where we would be at. Kind of looking back towards the south as we were before. And here you see this Blue Hill Shale exposed in the ditch and a little bit beyond the fence. And if you move up the diagram, you go as you change facies into the Codell sandstone, and eventually the top is made up of the Fort Hays limestone. I bring students to this stop to actually look at some other features that are visible within the shales and around laying on the ground that are weathering out of the Blue Hill Shale. The two things I'll point out are selenite crystals. XTALS is my shortened version of crystals, and something called septarian concretions. Well, both of these features are secondary. After the rocks have been deposited and buried, and they're being squeezed by burial, fluids move through those rock systems, and those fluids, of course, have elements dissolved in the water. It could be calcite, it could be a bicarbonate, it could be iron, it could be a number of different types of things. So as the water moves through the rock, if that water comes in contact with some type of a material, usually organic, that organic material causes precipitation to take place inside the rock. And so you get a brand new cluster of minerals forming in these zones, in these pockets. One of these secondary minerals is selenite. Selenite's a form of gypsum. Now the selenite crystal form is there in the inset on the bottom left-hand side of the slide, right below Blue Hill Shale, kind of a rhombic shape. And they come in different sizes, of course. And so I want you to remember that the secondary type of mineral caused by kind of a geochemical process are these selenite crystals. The second feature is another kind of thing that grows in place, where you might get silica or calcite growing into more of a ball shape. Kind of looks like a grapefruit maybe in size. And these things will get larger and larger. So what can happen to these concretions, as they're called, is that if the concretions end up in a position where they are below or above the water table, where there's no water, they dry out. And so they crack. Now what happens if the water table rises back up and you got groundwater percolating through and around and through these cracks of these concretions? Well, new minerals precipitate out again inside those cracks. And that little feature you see down there on the bottom right-hand side, the larger three-dimensional piece, is where you see those new minerals forming again inside of this concretion. Now, someone calls these things septarian concretions. The word septarian comes from septa. Septa meaning dividers. Like you cut open a grapefruit and you look at those little bound or barriers between the parts of the grapefruit flesh, those are called septa. We see those kind of septa in a variety of fruits these days and other things in everyday life. But since it's in these concretions, we call them septarian concretions. If you take a concretion and cut it open, the picture in the extreme bottom right is kind of you can see those cracks and they're filled in with different colored minerals. So two secondary features at stop 5 that are kind of things that have grown with time inside the Blue Hill Shale during the Cretaceous and after burial and subsequently even up until today. All right, let's move on to the map again. We're going to move north and west of our last spot. We're just along the Saline River. And this is a very special spot for me. And one of the classes I've taught here are structural geology. And I always bring my students in my senior classes out to this place that you see in slide 40. It's a place where it's pretty spectacular in terms of structure. Large segments of rock and blocks of rock are sliding and slipping downward. We refer to these as slumps. And so there's some pretty good slumps there within the Fort Hays limestone that make up the main cliffs. And underneath the Fort Hays, you know from previous stops, is the Codell Shale. And below that's the softer, weaker, Blue Hill Shale. So if we look at that and look at the mechanics of those rocks, let's go now from slide 40 and move to slide 41. A close-up of one of these slumps in an area along the Saline River. You can see that very top zone, the Fort Hays limestone. To the right of it, below, is the Codell sandstone. And even further to the right, you can make out a little bit of the Blue Hill Shale. But actually below this whole segment, down at the very bottom of the picture, is the gray, blacker Blue Hill Shale. Well, there's been a big curving break between these rock units where they slide down and slump. I have a picture coming up of a before, during, and after kind of diagram that I made that shows the mechanics of how this worked. Well, we know that if you go from Blue Hill Shale upward to Codell, upward to Fort Hays, you're going to younger and younger rocks. We call that going to stratigraphic up towards the top of the system. So we can really identify what's going on in terms of structural mechanics and also where stratigraphic up is, which is very important when we're analyzing rocks at the surface and the subsurface. So once we move to slide 42, on the left-hand side are those same slumps I just showed you before with the arrows showing stratigraphic up. But let me bring your attention to the right-hand side. The very top part of the schematic shows the brick limestones. Below that, the bricks of the Fort Hays limestone, the dots of the Codell sandstone, and all the white below it is the Blue Hill Shale. And so you see this kind of dashed line, this dashed curved line showing the potential for a large block to start moving downward in a curving manner and sliding and rotating until you get to the very bottom of the diagram. And the very bottom diagram is my graphic representation of what you see to the picture, the actual photograph exactly to the left of it. So this is kind of cool. It's great for structure, to teach students about structural geology, so that before we take them out west into Colorado and Utah, they really get a feel for how rocks can move during faulting in this case. All right, slide 43, kind of a little sidestep here, something different. Some of the things that get exposed in the Blue Hill Shale that weather out are these strange looking shapes. If you've ever had a pet and you've had to clean up your pet in the backyard or the kitty litter box, this is actually fossilized feces, fossilized doo-doo, poop, whatever you want to call it. Okay. Of course, after burial, the actual organics are replaced by real minerals, iron oxides, hydrous iron oxides, things like hematite and limonite, but the shape is still preserved. Well, the fancy scientific name we use for these fossil feces are coprolites. They're very interesting because they tell us a lot about the organism that passed that stuff out of their body. These are probably maybe from larger vertebrates that were in the Cretaceous seas. And I know that some of these coprolites, if they're large enough, can be x-rayed or can be cut in half. And you look at what it tells us, maybe something about what that organism ate. I always talk about, when I'm out here in the real field with my students, about a very large 2-foot sized coprolite that's related to a dinosaur. Up in South Dakota, they could x-ray and actually see the bones of a smaller vertebrate that dinosaur ate, that meat eater. So kind of interesting, strange feature, coprolites, fossil feces. All right, slide 44. Another interesting feature when we're out in this part of Ellis County is to talk about the oil industry. Ellis County is usually the #1 oil-producing county in the state of Kansas. And so what they do out here in this big oil field is they'll drill 3,000 to 4,000 feet down, 3,400 to 4,000 feet down through all the sedimentary rocks, and they run into some deep-seated sedimentary rock packages, one of which is the Kansas City Lansing system, which is the first oil-producing horizon they run into. They drill deeper and they run into another unit further down called the Arbuckle. So I would like you to remember a little bit about the oil industry here, that this is how far they drill down and they penetrate that. And of course, you can see in part of the distance here some pump jacks where they are pumping oil out. This is a pretty high, producing zone called the Bemis-Schutz oil field up in northeastern Ellis County. Kind of unique. All right, slide 45, moving further towards the west. This is going to take us to a very bizarre outcrop. And I'm going to spend a lot of time on this one, so hang in there. Kind of unique. This is on private property, and I'll tell you who it is, but it's my stop 7 in slide 46. And I've got an arrow pointing here to what's called the ash pit. This is actually volcanic ash. It was blown in from the west during a particular time period. So let's move to slide 47. This is a Google Earth image, and out in the Rocky Mountains in Colorado and Wyoming and New Mexico, there were volcanoes that were active during the Pleistocene. And just like when Mount St. Helens blew up in 1980, I was out in Kansas at that time, and the winds blew fine ash all the way to Kansas from Oregon and Washington when that volcano erupted. And so fine film of this glassy material developed. Well, back in the Pleistocene, there was a fair amount of ash that was wind-blown in and landed on the surface of western Kansas, out towards Hays in Ellis County. Now, back in the Cretaceous, some of that ash might have been deposited in the shallow seaway, or if it was, the sea level had dropped, it landed on the land. Now, of course, that's during the Cretaceous. During the Pleistocene, it was all above sea level at that time. And so this wind was blowing these ash deposits in from western Colorado, parts of New Mexico, and up in Wyoming. And we know that because we can do this tracing the different colors and textures and sometimes certain chemicals, elements that might be in this volcanic ash to where the source area was. So try to imagine back in the Pleistocene, you had these ash deposits laying on the surface of the land, and along comes some storms. Well, the streams fill up and the rainwater is taking and flushing this ash off the surface into the streams that we'll see in slide 48. Kind of interesting. And so Some of the rivers got choked up with ash and the river system changed its flow direction. I got the arrow here points to where that quarry is, and you can see that the river flows north of that in a different direction, kind of east and north of where the actual volcanic ash is. So slide 48 is kind of interesting. Try to get yourself wrapped around what was going on in the Pleistocene time. So let's move to slide 49. Another low angle view. He's flying over the ash quarry. This is on private property. It's owned by John Love, and he gives us permission to go out to the ranch and go into his quarry and take a look at the layers inside the volcanic ash. Not only that, there's a local company called APAC, and they make asphalt. And they come out periodically to the quarry with their trucks, get X number of truckloads and take it back to their operations in Hayes and use it as a filler to make asphalt. Kind of unique. So John Love gets a little bit of small amount of money for them buying the ash from him, and Apex gets, of course, a really unique silica-rich volcanic ash. It makes a very good binding agent in their asphalt. All right, let's move to slide 50. Get actually down into the quarry itself. It's very white, very powdery, very fine-grained. If it's a windy day, this stuff blows around, can get into your eyes, and if you're wearing contacts, can really mess it up. But the picture on the top right-hand side, you can see real thin layers of a chunk of this volcanic ash. The bottom left-hand side, you can see some burrows that filled in with darker, dirtier soil. Could be some mammal that was burrowing into this ash, long after it was deposited. Some of these are modern, some of these are ancient burrows. So I have some burrow types. Both these are modern, both on the bottom left and the bottom right. In the bottom right, on the left-hand side of that image, you can link this long, skinny brown line. That's a root, where a tree rootlet went down in there and it was digging into the ash, of course, to get down to the water table and get stuff. You can also see something weird, the very bottom right side of the whole slide, this black thing. That's a machete. I use that machete to carve and smooth away at the layers of the ash to start looking at the fine detail of that ash in there. And I'll show you a couple pictures of some of the things I could see because of that. All right, let's move to slide 51. In slide 51, I have a variety of images, mostly under a microscope or a scanning electron microscope, of what the textures of the glass fragments look like. Remember, this magma exploded out of a volcano. It was blasted 40, 50,000 feet into the atmosphere, and fine little fragments of glass are formed because of instant cooling of that magma. And of course, the ash takes on a color and a characteristic of the different types of material in that magma. And another thing I did was to take ash and have it X-rayed. The middle part of this diagram is an X-ray diffraction type of graph that I made here. I X-rayed this in Tamanic Hall and wanted to see if it had any mineral differences in it. It was pretty much all glass. That's a real typical up and down smooth pattern of lines that is quite representative of glass. But this stuff is pretty interesting under a microscope. Very sharp pieces of glass. Now, after I had smoothed off the surface of that, let's move to slide 52. Smoothed off the surface with my machete, I could actually see little crossbeds. These are caused by ripples and currents as the ash was moved along by the stream. And so with these crossbeds, I can figure out which way the river flowed. In other words, paleocurrent, kind of like paleomap, ancient movement of the currents in here. In this case, most of those crossbeds indicate a left to right kind of movement in their pattern. Let's move to slide 53. Taking a look at some of the burrows, I brought my depositional environments graduate class out here one year, and we were digging around. And in the very bottom of the quarry, we actually found an old, rather large burrow created by a Pleistocene-aged beaver. At least we think it is. It looks somewhat similar to known burrows, more of a corkscrew or spiral type pattern that you can see in a black and white picture in the bottom right-hand side of that. We were hoping to actually come back and put some preservative on this and try to dig it out and bring it back to campus, but When we finally got back to the quarry a couple months later, APAC had come out and removed ash for their stuff. So all I have is photographic evidence of that. Let's move on to slide 54. Again, some modern burrows. Some of these might be rabbits or other things, maybe badgers that live around here and burrow in and make their homes in this ash material soft enough to dig into. And of course, soil would, kind of fall down into the burrow and fill it in later on. Slide 55, a different kind of event that went on here. I actually did what's called a seismic refraction survey. I had a tamper that I could pound the ground with, and then I had a geophone, and so I could record what we call time travel curves and figure out patterns in here. And I won't go into a lot of it, but I was able to see the layers of the overburden, OB in those kind of schematics on the right-hand side. I could see the thickness of the volcanic ash because of its specific velocity, and I could see what was underneath it, the bedrock, or BR, in those diagrams. So when I got done, I was able to use a modeling program in this thing to create a model of the surface, an ancient surface of what it looked like. And it turned out to be a meandering stream kind of shape and pattern. So the paleo surface, or ancient surface, that you see on the very bottom slide is what the ash filled in, and right above it you see the present surface map, but part of the actually kind of rectangular quarry in the very middle of that present surface in there. So kind of an interesting geophysics approach to looking at science in this slide. Let's move to slide 56. Again, I want to remind you this is private property. The Love Ranch volcanic ash. There was something different I started seeing in the layers. It was really unique as years progressed and more exposures, as APAC came in and removed more ash, I could see new things every year that developed in here. And I'm referring to them as seismites. I had a colleague of mine, worked with the Kansas Geologic Survey, and he and I looked at these kind of warped. This gentleman's name, by the way, is Dan Merriam. He's a retired faculty member at KU right now, Kansas University. And he and I were looking at these layers and how contorted they are. On the right-hand side and on the bottom right-hand side, you can really see the curviness and waviness to this. Well, we want to take you back in time to when the ash was first deposited in the stream, when it was very, very wet. It's known from other research that when wet sediments, clay, fine sands, fine-grained material like this is wet, and you shake it really hard, it goes through a liquefying process called liquefaction. And what we think happens here is that there was an earthquake that occurred in Kansas, and these wet ash deposits actually kind of got all liquefied and contorted during this seismic or earthquake event. And so these are called seismites in our terminology, and so we thought something new and unique was actually preserved in the rock record that you see in slide 57. All right, moving on to slide 45 here now as we move on. Not sure if my numbers are out of sequence. I'm going to jump back real quick. Yeah, I got some numbers kind of mixed up here, but that's okay. Slide 45 is this map again. That shows our very last stop north of Ellis, and we'll move into slide 58. Kind of a mix-up on the numbering of slides, folks, but that's okay. I think you can follow along. This is our last kind of field stop per se of the day, and it's a stop that's kind of unique for a couple of reasons. First of all, from the geologic standpoint, on the right-hand side of this image, you can see a white kind of brownish outcrop. This is the Ogallala. The Ogallala is kind of a concrete looking, very hard in places, very soft in places type of deposit. It's fairly young in terms of time. There was mountain building activity going on out in Colorado for what we now know as the modern day Rockies. So time-wise, during the late Cretaceous up into a Miocene epoch time period, there was a lot of sediments being shed eastward off of the present-day Rockies. Kind of a big package of rock we call a clastic wedge or an alluvial fan. Alluvial refers to river deposits. So here's these fast-moving, kind of sinuous rivers flowing off the Rockies, carrying lots of sediment, and depositing them eastward. And of course, those deposits became what we today call the Ogallala. And from fossils in there, fossils in there indicate that this is probably a Miocene-age deposit. And so in this outcrop, there are some of these rock layers that are very porous and very permeable. So that makes this a really good kind of what we call an aquifer. It can store water. And I'll say a little bit about that in a subsequent slide. So one of the things I need you to remember for this particular kind of outcrop, so to speak, is the formal name, which is Ogallala, the age of that deposit, which is Miocene. That's an epoch name. It was deposited in what we call a clastic wedge or alluvial fan by river systems. And then the event, the mountain building event that took place between the late Cretaceous and the Miocene is formally called the Laramide orogeny, after Laramie, Wyoming. So a little bit of tectonics involved in here, a little bit of depositional environment terms that I want you to remember about this outcrop, and a little bit about the aquifer concept I'll bring in to play one more time. Before I leave slide 58, though, I want to point out in the outcrop on the right-hand side, the more white layer. The arrow is pointing to a little white zone. It's very narrow. And this is actually a small lake or a pond that was off the main body of the river system. And so these are actually lake deposits in here. And so if we move to slide 15, I think it'll be in slide 60 coming up here, something about those lake deposits. Let's move to slide 59. In the top right-hand side, you see a common exposure of what the Ogallala looks like, and see how porous it is, and makes a really good aquifer when it's underground. So the map on the left-hand side, the shaded in area represents how far you can find the Ogallala from all the way down into Texas, all the way up into South Dakota. It's an aquifer system that's used by these states to grow all kinds of crops out here in the West, and it's being used more, and this is a big debate today as to water supplies, not only in Kansas, but in all of these states that utilize water out of here. Well, these were the sediments, the Ogallala is where it was deposited. Let's take a look at the bottom right-hand picture on this slide, and it's just a close-up of Kansas itself. Ellis County is kind of right in the middle. There's a few little fingertip pieces of the stippled area, the orange or brown, whatever color comes through on your screen, that kind of go just to the left of the K in the word Kansas. That would be roughly where Ellis County is. So there are small exposures of Ogallala close to the surface and at the surface in Ellis County, but it's not really a big aquifer out here in Ellis County. The aquifers are more west of us and southwest of us in Kansas. But if we move a little bit west, we'll see that there is some aquifer that's used in a very interesting way. But before I get there, I want to talk about that lake deposit. I have the students go over to that little white layer and get up close and look around for these casts of freshwater snails. Now, snails are a type of gastropod. They're kind of coiled little gastropods that lived around the edge of the lake, and of course they got buried when they died, and then they got infilled and preserved as a fossil. So here we have a Miocene lake deposit with freshwater snails in there, and it's kind of unique. There are other kinds of fossils preserved in the Ogallala and other interesting things about the Ogallala that I'll maybe hold off on to in the future in a different kind of totally virtual field trip. So all these freshwater gastropods are located in slide 60. All right, now just a couple more slides left before we are done today. Let's move to slide 61, another Google Earth picture. And this is kind of moving a little bit west and out of Ellis County into Trigo County, just the northeastern part and eastern part of Trigo County. And there's a town out here called Waukene. Waukene gets its water supply out of the Ogallala. And there's some big water towers out there and a bunch of pumps and pump that water in there. And so I have an inset on the right-hand side that's an outcrop exposure of the Ogallala, just on the south side of the Saline River. Not northeast of Waukene, and the inset picture on the left-hand side is part of the pumping system material. And what's interesting about the water out here, it has a certain chemistry to it, certain kind of character. Now, the city of Hays gets most of its water supplies from wells from Big Creek alluvium, or a river system south of Hays called the Smoky Hill River. Those are the two main sources. We get nearly all of our water out. We might get a little bit of water out of drilling down and getting something into Dakota, but today the city of Hays gets most of its water from Big Creek alluvium or the Smoky Hill Creek alluvium. And it has a certain chemistry to it. There's a more calcite-rich character to the water from Big Creek and Smoky Hill. The water out of the Ogallala, northeast of Waukene, is different. So think about this. Water has different chemistry. So if you're a beer lover, let me tell you the rest of the story. If you come to Hays, there's a microbrewery, LBT, that's located in Gella's Diner here in Hays. The microbrewery makes its own beer. So let's go to slide 62. You can see in slide 62, it's inside the restaurant and bar and microbrewery. Well, the brewmaster has decided that he feels that the chemistry, the water from the Ogallala, is better fitting for the types of beer that he wants to make. Well, it must have proven well, because he's had lots of medals for different types of beer styles that he has produced out here. So if you ever get to Hays someday, go on down to Gella's Diner and grab a really good microbrew, and you'll be think back what I told you about where the water comes from. And so someday I might have another totally virtual field trip about the geology of beer. And we'll get into much more detail about geochemistry of beer and how it's made, and some of the different types that occur out here in Kansas and other parts of the world. Let's move now into the last slide. I'd like to make some acknowledgments to people who helped make this field trip happen. Mr. John Love, of course, always allowing site access to that volcanic ash. And certainly to Mr. Gerald Wyman, he's the LB brewmeister at Gella's. And of course to Mr. Schmidt, who allowed us to go into the property to see those gravestones out there. So, you always need to remember that you want to thank people for allowing them access to their property or to their information, things they can help you with in learning a lot about the geology. So we're done with the trip today. I hope that you've enjoyed this trip. And again, as always, if you had a chance to get out in the real field, please do that. So before you take the test, be sure to review your notes and log into Blackboard and take the exam and go back to that first slide so that you understand all what's expected of you to successfully complete this class. So I thank you again. Hope you had a good time, and you take care. Bye-bye.